So what is the improved or the other algorithm we are talking about here? The alpha beta pruning algorithm. What the pruning means here, it eliminates a branch of a search tree from the consideration without exhausting examination of each node. The basic idea is to prune portion of the search tree that cannot improve the utility value of the max or the minimum. So here we are basically eliminating a particular portion of a search tree that cannot improve further the utility value and but just considering the value of a node seen so far. So how the alpha beta pruning is used? It is used on the top of a minimax search to detect paths that do not need to be explored. Right? We will simply eliminate the part that need not to be explored, and the max player is always trying to maximize the score and the minimum player is always trying to minimize the score. Obviously, how we are saying that the max player is always trying to maximize the score and the minimum player is always trying to minimize the score, because the opponent will perform the opposite function only when we are talking about the two-player games. So alpha cutoff or the beta cutoff given a max node and cutoff of the search below doesn't generate any more n children if the alpha of a particular node is greater than or equal to the beta node, or alpha increases and passes beta from below. And what is the beta cutoff here we are talking about? We will see here in form of examples, right? So it will enumerate the further searches. We are starting from the max, minimum, the max, minimum, and at every level we are talking about the alpha and the beta values. Let us set up the phase assigned to each left most or the right most internal node of a tree variables alpha infinity and the beta plus infinity, minus infinity and the plus infinity हमने value assign कर दी है, whether to a left node or whether to a leaf node. Now, what we will be done, look at the first computing final configuration value, which is 3 here. It is 3, parent is a minimum node, right? And so that the beta minimum value to be 3 here, right? So here the minimum value will be 3, the beta minimum value will be 3. And now what will be the other value? Then we will look at the next value 5 here, right? Since the parent is a minimum node, we want the minimum of a 3 and a 5, which is 3, and the parent minimum node is done with a fill alpha value of its parent maximum node here. So alpha node की value क्या है आपकी 3. Now always set alpha for the max node and the beta for the minimum node. Now we have decided we will set alpha for the maximum node and beta for the minimum node, right? And copy the state of a max parent node into the second unevaluated minimum child. Here we have to copy the state of a maximum parent node into a second unevaluated minimum child. So what we have done the other child node, we have assigned the value 3 here, and in the another child node we have assigned the value 3 here, alpha value 3. So to copy the state of a max parent node into the second unevaluated minimum child here. Okay, then look at the value, look at the next value. We will find the next value is a 2 here. How the 2? Since the parent node is a minimum, we will again assign the beta value as a plus infinity. 2 is a smaller, then we will change b here as a 2 here. Here we have changed the another value 2 here. Now what we will done? Now the minimum parent node has a maximum value. Now the minimum parent node has a maximum value of 3 and the minimum value 2. Now we have both the values here, the minimum value also and the maximum value also. The value of a second child does not matter. Definitely the value of a second child does not matter if it is greater than 2. How? We can see here in the example, we have see whether here first child value is 3, right? And the another child value is 2. So when we are talking about the other child value in this case, right? We have deleted the other child value. Why? It doesn't matter to us because it is not greater than 2. If it is greater than 2, 2 will be selected for the minimum node. So definitely the value of a second child does not matter. If it is greater than 2, 2 will be selected for the minimum node, and if it is less than 2, it will be selected for the minimum node only. But since it is less than 3, it will not get selected for the parent maximum node. Here also does we prone to the right subtree of the minimum node and propagate the max value up to the tree. So here we have seen the example, and everywhere when you are getting this symbol, that means it doesn't matter, or simply we are using the prone function here and the pruning here, where we are eliminating a particular search tree because there is no need of it, because we are comparing the values, and according to that we doesn't need any value here. Right? Why we doesn't need any value here? Because the other node here is the maximum node, and we need the maximum value only. And if the 2 is here, that means it is a value, then another child value doesn't matter here because it is definitely will be greater than. So the 3 is greater, and we had already assigned the value to the maximum node here 3. So we will eliminate this particular portion of a search tree, or we will prune this particular portion of a search tree. So this has been explained in this graph, and the max node is now done, and we can set the beta value of its parent and the propagate the node state to sibling the subtree leftmost path here. So here we have decided about the leftmost path, and the next node is 10, and 10 is not smaller than 3, so the state of a parent doesn't change. How we are considering, we can see here. We can see here we have eliminated this because we will move to the further. And now again in the next example you can see here, so the next node is 4 here. Again, when we are evaluating each function here, we will see the 10 here again. So the smallest value goes to the parent minimum node and minimum subtree is done. तो ये एक बार सर्च ट्रीज जो मैंने शो करे आपको, ये सब आप देख लीजिएगा, and you will be able to find the solution, and you will be able to see what has been eliminated. We have eliminated here this node. We will eliminate further nodes because we are talking about here the leftmost portion only. So here further nodes will be get eliminated, and after combining the propagating value up to the tree, modifying the corresponding alpha beta value, also we will propagate the state of a roots node down to the leftmost part of a subtree, because we have assigned all the values to the leftmost path here, and we have calculated with the help of a utility function first the leftmost path. We will consider first the leftmost path. Again here another changes will be there, and after that according to that we will decide which particular portion of a tree we should be eliminated. So here you can also see all the right part here we are eliminating, or we are pruning from a search tree, right? So here we are just talking about the left portion of a tree of a child. Finally, no more nodes remain when we will traverse, and we will propagate the value up the tree. And now the root has a value 3 that comes from the leftmost child, again from the leftmost child, because at the end we need to perform the maximum function, and thus the player should choose the leftmost child move in order to maximize her winning, right? So when we are talking about a leftmost child, then we are talking about the player is maximizing his turn to be win, and when we are talking about the minimizing, the player is minimizing the other player's chances to win. So as you can see, the result is same as with the minimax example, but we do not visit all the nodes of a tree. Why we do not visit all the nodes of a tree? We have not traversed all the complete tree. As you can see here in the second child node, after the 2 node, we have not visited the rightmost portion here. And in the leftmost child node, we have not visited the rightmost portion here. Sorry, the rightmost portion we have not visited in the 2 second child here, and the At the first child, whose value is 3, we had not visited the right portion here because we had taken first the left value, and after comparing the values according to the min-max function, there is no need to traverse this particular portion of a tree, as the result is same, but somewhere the time has been reduced. The result is same as with the minimax example, but we do not visit all the nodes of the tree. So with the help of a alpha beta pruning algorithm, we had further improved our minimax problem here.